Right, okay, so as you can see, you have a logic gate there, which is clearly a NOR gate, but then it says complete the table. So think about what's going on. When switch S1 is open, the current will obviously come down here, and it will go that way, won't it, when the switch is open. So if the switch S1 is open, then A would obviously be a logic 1, wouldn't it? Switch S2, if switch S2 is open, the current cannot go any further than this. So because it can't go any further than that, you're left with a logic 0 there. Obviously, trace it for, finish for all of them. Q is obviously the NOR gate. You must know your logic gates. And obviously the LED, the only way that LED will turn on is with the logic 0 there, because you've obviously got 5 volts. Remember, you need a potential difference, a voltage difference between there and there. So the LED will be on when Q is a 0. There are your solutions there, so please have a look. You can see Q is a 0, LED is on. Okay. Okay, simple Ohm's law question. Can't believe they give you 4 marks for this actually. Forward volt drop is 2 volts. Logic gate is 5, which leaves 3 volts across the resistor. So if you've got 3 volts across the resistor, 14 milliamps, it's quite simply Ohm's law, isn't it? So R equals 3 over 14. Don't forget, if you use milliamps, it will come out in kiloohms. And then your preferred value, because you're limiting, you want a maximum current. So for the preferred value, you always go for the one above it. So here are your solutions. You can see there 214 ohms. So we select the one above it, which is 220 ohms. Okay. Part A, you need to know your logic gates. I'm hoping you know what logic gates they are. You've got a NOR, an AND, and an OR gate. Then can we convert to NANDs? Dead easy. Convert it to NANDs, cross out your redundant gates. Describe of converting to NANDs. Well, obviously you need less ICs, don't you, if you convert to NANDs? And in fact, you might be able to say exactly how many you would need. Oh, I've not actually written that on there. Cancel. Sorry, cancel the 2 in the line, so that would cancel with that, and that would cancel with that as well. Okay, 1, 2, 3, 4, 5. You would need 2 ICs, and you would need 2 ICs if it was NANDs. You would need 3 ICs without converting to NANDs. If this was a first year paper, I'd take my time and go over the Morgans a little bit, but I'm hoping you know split the line and change the sign, which I will show you in a moment. There's your truth table for part C. Put the ones in, do your groupings, get your answer. So let me show you the solutions for those. Okay, just have a little look there. Let's get the laser pointer, shall we? So you can see split the line, change the sign, double knots cancel. So you're left with that. This is a Boolean identity, but if you multiplied this not A into that bit there, you'll see that the not A or A would cancel. So you'll be left with that. So it's 3 easy marks. Put the ones in. You've got 3 groups of 2 going off there. So there you go. There are your 3 groups of 2. Hopefully straightforward. Okay, a couple of ways to find resistors in parallel. You could just do obviously 1 over R1, 1 over R1 plus 1 over R2 equals 1 over the resistance. Make sure you do 1 divided by the answer. Students, so many students just do 1 over R1 plus 1 over R2 and just leave it there. Look, that's not the answer, it's 1 over the answer. So you have to therefore press 1 divided by answer in your calculator. Another way you can find resistance in parallel is only works for 2 resistors though, product over sum. So if you actually did the product R1 times R2 divided by the sum R1 plus R2, that would actually give you the same answer. I don't go over that one because it only works for 2 resistors. If you have 3, you can't do that. So that's why I don't bother showing you that, but it is there if you want to remember it. Product over sum. Okay, and then once we know that, we can find the currents. Just make sure we remove 0.7 volts. So it will be I is V over R, so it will be 8.3 over the total resistance. Okay, I'll show you the answers. So you've got 2.3K for the product over sum, and then obviously you've taken off the 0.7 volts there, and then it's obviously just your bog standard ratio. Sorry, not ratio, it's bog standard Ohm's law, V over R. Okay, 1.84 milliamps. Okay, determine the voltage V out. So the voltage across there is going to be obviously the voltage across the diode, which is 0.7, plus the voltage across there. How do I find the voltage across there? Well, if you know the resistor value and you know the current, you can work it out just doing V equals I times R. The power dissipated in this resistor, you could just use V times I, or you could use I squared R. So whatever the I is, multiplied by your square it and multiply it by 2.2, and then determine the value of V out when the diode is reversed. Well, if the diode is reversed, no current is flowing, so you can look at all of this bit as an infinitely high resistance. If you've got an infinitely high resistor and a lower value resistor, majority, if not all the voltage will be across there. It would read 9 volts. Okay, so just have a little look. We're on part 3, part 4 and part 5. You can see that you've added the 0.7 there and the voltage across R3. You can use I squared R, or you could use P equals VI, and then obviously V out is 9 volts. Straightforward. Okay, say what you see. If B and A are both zeros, D0 gets through. So the 0 volts is getting through to Q. LED will be off. If B is a 0 and A is a 1, that's going to be the number 1. So it should get through and it should be flashing at 4 hertz, 4 cycles per second. The LED will be flashing. If the number 2 gets through, LED will be on and remain on. And then if D3 gets through, it will be flashing, but it's half of the frequency. So it will be flashing at a rate of 2 hertz, 2 cycles per second. Okay. Show you the solutions for that. Yeah, flashing at 4 hertz and flashing at 2 hertz. So that's where you get 2 marks for that one to actually say the frequencies. Okay, the advantage of a multiplexer for the previous question is obviously you can reprogram it by changing the logic at the inputs there, so you can reprogram them. What does TDM stand for? Time division multiplexing, and then explain how this communication system achieves it. Well, you've got a binary counter going on there, so you're going to select one of those channels, or each of those channels individually. They'll be given a specific time, so you can get more than one channel down the same data link, and then give an example. So for example, it will be if S1 is a logic 0 and S0 is a logic 0, channel 1 will go down. If S1 is a logic 1 and S0 is a logic 0, channel 2 will go down, etc. There's the solution for that one there. Okay. Okay, some nice easy ratios. I've left the answers up there, but just to show you how to do it mathematically, the voltage at Y is the voltage there. So there's going to be 10 lots of the total 10/25 of 15. Okay, 6 volts. Okay, and then the resistance of this LDR here. Well, if we know when it switches, we know it switches when X goes past Y. So if you've got 6 volts there, you have 9 volts there. I mean, I can look at that by ratios. I know that this is going to be 50% higher, or in this case it'll be 3.3. However, if the values are a bit difficult, then just quite simply the current through the first bit equals the current through the second bit, the resistance that we don't know, resistance LDR. Okay, there's one unknown there. Rearrange the equation. Remember, if you flip one side up, you can flip the other side up, so it's basically 2.2 over 6 times your 9, 3.3. Okay. Describe the behaviour of both LEDs as the light level changes. So start with this either being light or dark. So if this is dark, if it's dark, the resistance is high. If it's dark, the resistance is high, which means the voltage there is high, which means the voltage at the bottom is low, which means obviously Y, the voltage at Y will be higher than X. So if it's dark, voltage at Y will be higher than X. So therefore, op-amp saturated negative, and the green LED will be on, or saturated to 0, green LED on. It's saturated to 0 there. As the light level increases, the resistance goes down. Eventually, X will be higher than Y. When that happens, the op-amp saturates positive, and the red LED will turn on. Okay, so this one, again, I've got the answers on there for you, but hopefully straightforward. Complete circuit diagram about adding the component to protect the MOSFET. That's obviously your diode, like that. Make it neater than me. Power is power in the MOSFET is I squared, so it's the drain current squared multiplied by the resistance between the drain and the source when it's on. So you must have been given that, yeah, drain and source resistance, and ID is 8, isn't it? Not that one, because that's the max. Okay, so you can see on the mark scheme there, that's the answer. And then the other one is just VGS. Use the equation on the data sheet and plug the numbers in, and you should get the right answer. So you've been given GM, as you can see. You want to find VGS. Of course, and we know the drain current is 8. It's as simple as that. Okay, a bit of Thevenin. Remember how to do this. So first thing is we just do a potential divider. Derived when the thermistor is 2K. So first thing is potential divider to find V out. That's dead easy. With 2 lots of the total. If that's 2K and you've got 2.2K, with 2 lots of 4.2. So 2 divided by 4.2 times your 10. ISC, remember, short circuit, short out the bottom resistor, or in this case it's thermistor, so short that one out and just use Ohm's law, and then you can draw your equivalent circuit. So that's 4 marks. There you go. So we've done that, we found the equivalent resistance, and we've drawn the equivalent circuit. Okay, hopefully straightforward there. Just put the answer on this one just so you can see it. So input resistance of 5.6K, so that's that one. So how I would find the voltage across the load, which is obviously the voltage there, I would probably just go for ratios, to be honest with you. So 5.6 over the total, which is 6.65 times your 4.76. That's how I would do that. They've done a different way, but I think I'd be tempted to just do what I've done there. Okay, and then this one's dead easy. Remember this one, load current of 200. The Zener diode needs 10. It's just Ohm's law, look. So easy, Ohm's law. 210 milliamps, dead easy, dead easy. What's the voltage across there? 5 volts. What's the resistor value? 5 divided by your 210. Let's show you the answer for that. Gives me 23.8 ohms. You can see across there, 23.8 ohms. but then obviously it says the ideal value for that one. Okay, so we'd probably want to go. Oh, it does say except 24. It does say except 24 range. Okay, fair enough. Actually, it doesn't. Yeah, it doesn't say select from the E24 series. But if you were, you'd actually go for the one lower than that. To be honest, so I'm surprised to say except 24, but they do. Okay, bog standard potential dividers. So I know the voltage there. Don't need a calculator for that because look, 2K, 2K, it's 10 volts. We know it's 5 volts there. So Vy equals 5 volts. Vx equals potential divider 1.95 over the total resistance, which is 3.96 times your 10. Times your 10. 4.924. To be honest with you, you could probably leave it like that. Okay. And that's in volts, obviously. Right, which one's a higher voltage, Vy or Vx? Well, Vy is higher, isn't it? That's going into the plus sign. So the answer is going to be positive. How many times bigger is the output going to be? Well, there is an equation on the data sheet, but I know the gain is 100. So I know it's V diff times gain equals 100. Okay. Now, if you leave this in your calculator, and I go 5 minus answer, then you actually get 0.0776, if you see what I mean. If you don't leave in your calculator and you just rounded that, then obviously it would be 8 volts. But if you keep it in your calculator, it would actually be 7.60 volts. 7.60 volts. That's what the mark scheme says. I think myself, if you rounded that, you would be okay to put 0.8, 8 volts even. Okay, the equation's there. V diff times gain, which is RF over R1 equals V out. That's where that's come from. Okay. Okay, nice easy one here. And that's your DAC. Remember, DAC, always work out the first resistor A, and then you half, half, and half for the others. It's giving you this. It tells you logic 1 is 8 volts. And obviously, what is the voltage at X if I just put logic 1 in? Put logic 1 in. Dead easy. Find your gain. Well, V in times gain equals V out. Yeah. V in times gain equals V out, doesn't it? So 8 volts multiplied by the gain, which is minus RF over R in, so minus 10 over 320 equals minus 0.25 volts. If I now flip it, there's a gain of minus 1, so flip it, 0.25 volts. What would it be if the number 6 is pressed? Well, 6 times, and it's V out as well, 0.25 is equal 1.5 volts. There you go. Dead easy. Okay, so obviously a grey code is put onto the inputs. There you go. The resolution was 0.25. So essentially, I'm not going to draw all of this. Essentially, oh, there you go. There's the answer there anyway. But just draw one of them in for you. So if you've got starts with 0 there, and then 1 is 0.25. So it's always going to go up to there, isn't it? Then it goes up to number 3. Well, what's 3 times 0.25? Yes, 0.75, etc., etc. And you can see it looks like this. Lovely jubbly. Okay, so we have a bit of a weird one here. But we're talking about difference between a surface wave and a space wave. Okay, we've not really done a lot on this. Surface wave would go from the transmitter around to receiver following the surface of the Earth. A space wave would go up into space and then back down to the receiver. So I'll show you the mark scheme in a minute, but if you draw those on. This is just C equals F lambda. So you've been given lambda, you've been given C. Can you find, we've been given F, and we've been given lambda. Can we find F and C? Can we find lambda? So C equals F lambda, rearrange that. This is dead easy. We always do this. Frequency spectrum. Frequency spectrum means line. So stick a line in the middle, a line for that side and a line for that side. Make sure you label it. So 200k in the middle, 204, and then 196. It's that easy. Let me show you. You can see the space wave there. You can see the lambda equals C over F. And you can see the frequency spectrum. Okay, determine the bandwidth of the transmitted signal from the previous question. So it's going from minus, well, 4K either side, so it's double that, so it's 8K, that's the bandwidth. This is an FM1, modulation index, you've got the equation on the data sheet, it's that beta 1. Bandwidth you've got underneath that, so there's a couple of easy equations you can use. This comes up quite a lot, doesn't it? Dead easy. The advantage of AM over FM, there's not many. The main one would be it's got a lower bandwidth, so you can get more stations on the band, on the entire band. Yeah. Whereas FM, because the bandwidth is a lot higher, you don't get as many stations on that band. Okay. Or stations in that frequency range. Okay, I've just got the mark scheme up for this one. This is one of the QER ones, quality for extended response. Before that, let's just have a look at this table. Basically, apart from output impedance, obviously we want that to be low. Think about it logically. Low impedance means infinite current. So output impedance is low or 0. We get as much current as we want. Open loop voltage gain wants to be high or infinite. And the common mode rejection ratio wants to be high as well. So that's basically we want it to do the difference mode, to amplify the difference in the voltage. Yeah, not do the common mode. Okay, right, how would we calculate the gain bandwidth product? We have done this before. Last year we did it using Excel. So essentially, if you haven't got Excel, you're doing it in reality, then obviously you're going to need an oscilloscope, you're going to need an inverting or non-inverting op amp, and you're going to need a SIG-gen. Set the inverting op amp up, keep the gain fixed obviously, and then you're going to change the frequencies, and then you can observe V out on the oscilloscope and you can plot a graph, can't you? Essentially, when you plot a graph of frequency against V out, or V out against frequency should I say, eventually you'll get a drop off, and then when it gets to 70%, that will be your bandwidth. And then if you know the gain of the thing, of the op amp, just do gain times bandwidth, find your gain bandwidth product. So provided you get all that, you can write it in bullet points, but I hope that's straightforward. Yeah, you know the sort of shape of the graph it should produce, don't you? I'll just sketch it again. Yeah, the shape of the graph. You can even show it if you want. It's the one where if you've got frequency against V out, essentially it would do that. 70%, yeah, 70%, and then there's your bandwidth. Okay, and then obviously if you know the gain, gain bandwidth product equals gain times bandwidth. Nice. Okay, so this one we've been given a circuit to design, gain of 25. Oh, it's so easy, isn't it? So non-inverting op amp. Resistors always go to the inverting input. Remember, the only time you ever put resistors to the non-inverting input is when you're drawing a Schmidt trigger. Okay, so shall I sketch it? Let's get a pen out, why not? I mean, I'm hoping you've all got 5 marks here. If you haven't, and what have you been doing for the last 2 years? So be in that one. Okay. And then obviously gain of 25, make that 24 kiloohms, make that a 1 kiloohm. Yeah, that easy. Right. Power supply plus or minus 14, saturates at plus or minus 13. What will be the maximum input voltage? Well, if the maximum output voltage is 13 and the gain is 25, surely the maximum input voltage would be a 25th of 13. Yeah? Okay, so 0.52 volts. Okay, 7 marks. Okay, I'll just talk you through this bit. 5 volts per microsecond slew rate, so obviously it's going to go up. 1 microsecond later you'll be at 5 volts. Draw a straight line with your ruler, stop at the saturation which was 13 and go across. Dead easy. And then this one's just using the slew rate equation to find the frequency, so you just need to rearrange the slew rate equation there. So you've been given the slew rate, yeah, 5 volts per microsecond. Make sure we need to convert that now into we need to convert micro into seconds. So we times it by 1,000,000. So that should be 5 times 10 to the 6. So that might be where students mess that one up. So it's 5 times 10 to the 6 divided by 2 pi v. Okay, and there's your answer there. Okay, 64 kilohertz. Okay. Okay, so we've been given a communication system. Each channel has a signal bandwidth of 3.4K and a 0.5 guard band, given a total channel bandwidth of 3.9. Okay, each twisted pair has a bandwidth of 250K. Twisted pair cables reduce crosstalk. What is meant by crosstalk? It's basically when one cable can interfere with the other one because they're twisted. So if you've got a signal travelling down one pair, it can induce a current in the other. Okay. How many channels can be transmitted along one twisted pair? Well, the bandwidth is 250K and each channel is 3.9, so do 250 over your 3.9, but make sure it's rounded down to the whole number. And this one's your classic noise signal to noise ratio, so let me show you the answers for those. Okay, so basically you've been given 38 decibels. The equation is there. We want to obviously find the signal power. So we've been given the signal to noise ratio, and we've been given a noise. Okay, so we can rearrange that. PS, rearrange, and you will get that value there. You guys are quite good at all of that stuff anyway. So well done. Okay, so ideal value for R to achieve the break frequency. So break frequency, F equals 1 over 2 pi RC. So there's one unknown, which is the R. So basically R goes up, it's like an L shape. R goes up to the top, F goes down, they swap positions. So R equals 1 over 2 pi FC. So you've been given all those values, press equals on your calculator. 3 marks, wow. This is dead easy. Remember this one. So we want to work out the reactance and then the output voltage. Reactance is XC. XC is 1 over 2 pi FC. Once we've done that, we then, to find V out, we need to find, remember this one, the impedance, the Z value. So remember there's a triangle. Remember, because they're not, there's 90 degrees phase shift difference, phase shift. So you have to find the Z value first, which is on the data sheet. So the first one then, that's dead easy. We're just rearranging that to make R the subject. Next one, XC first of all. Work that one out to be that. And then notice the Z value, it's the square root of R squared plus XC squared. Do all of that. And then once you've done that, you can find V out. Because V out would be, it's like a potential divider. It would be this resistance, which is XC, over the total resistance, which is Z. So it'll be XC divided by Z times your V in, and your V in is 9 volts. Okay, we did quite a few of these, and remember you guys are really good at these by the end. The answers will be on the next page of this, but basically transistors work by putting an input current in, timesing it by a current gain gives you an output current going down there. So if you know the output current and the input current, we could obviously plot a graph and find the gradient, which will obviously give us the current gain, won't it? So on the next page, that will be shown. Okay, so this is where we plot the graph and then we can determine the current gain. Plot the graph, gradient, and you should get a range of between 115 and 125, but hopefully it's straightforward. You all know how to plot graphs. You've been doing that since maybe year 5, year 6. Okay, so remember this, the old classic off, active, saturated. Okay, so when a transistor is saturated, there is 0 volts across it. Vout equals 0 volts when it's saturated. So it's got to be 3.4 volts. And an ideal value for RB in this, and then the suitable, give a suitable preferred value. Well, basically we work backwards, don't we? So we work out the current going down here, take a 70th of that current because the input current will be how much less, and make sure obviously 0.7 volts is there. So when the transistor is saturated, I said 3.4, didn't I? So there'll be 2.7 volts there. So dead easy then. I'll put the mark scheme on, but basically we're finding the current going down there first, taking the 70th of that current, and then you can find RB. So find the current, there you go. Take a 70th of that current, there you go. I've done the minus 0.7, so there's your resistor value there. And then obviously you'd always go for the one lower, because if you went higher, if you went for a higher value resistance, there won't be enough current to saturate the transistor. If you went lower, there was still going to be enough current. Okay, so that's why you'd always go lower than the calculated value. But we've done a load of these, if you remember, a load of these calculations. I've done video on this as well, so thank you.